Dear students, welcome back to my YouTube channel MCBChemTube. This is an online chemistry tutorial and you get my previous videos either from my personal homepage or from my YouTube channel. We were discussing about the topic addition and elimination reaction from the part reaction mechanism in organic chemistry, and today I am going to discuss with you the stereochemical aspects of even and E2 elimination. And we already discussed the mechanism of even and E2 elimination in my previous tutorial. You can visit my previous video on this topic. And in this particular example, I am focusing on stereochemistry only. So we will discuss this stereochemistry by giving one general example like this. This is an alkyl halide and there are two carbon atoms. The first carbon atom is attached to different atoms with one leaving group. This is alpha carbon atom and this is beta carbon atom, and beta hydrogen is attached here, and in the presence of base, this base abstracts this hydrogen by kicking off this halide leaving group, and it gives alkene. And to get eliminated, one precondition should be there. The condition is the orbitals, that is overlapping orbitals like base orbital and CH sigma filled CH sigma orbital and empty carbon leaving group antibonding orbital. That all these orbitals should be oriented in same plane. For proper facing should be there. Okay, and this hydrogen and leaving groups, there should be anti and coplanar for proper orbital overlap. So you get corresponding alkene, and with a BH base get abstract, this gets one proton here, H plus here, and from BH, and there's a leaving group here. Okay, so we can predict the stereochemistry of the product. It allows the prediction of whether this stereoisomer E or Z is formed. So we will look into some example, and it was found that the stereochemistry of E2 reaction is stereospecific. So one particular isomer give only one stereospecifically, one, not more than one. And this can be evident from my following examples. And in this particular example, you can see that there are two carbon atoms. That is, this one is alpha carbon atom, and this carbon is attached to halogen. That is why it's alpha. And this one is beta, and there's a hydrogen on it, beta hydrogen. And here you have a phenyl group and one hydrogen in wedge shape, sorry, in dash. And here there is a methyl group in dash, and it is pointed upward. And this one is in wedge, and this one is in dash, pointing upward. And two phenyl groups are in same plane. And first we will write the Newman projection of this compound, and we are looking at this molecule from this side, suppose, and we can say this is the first carbon. We are drawing here this carbon, beta carbon here, and if you are looking at this molecule from here, the methyl group will be at the right side of your eye. From it will be here, and bromine will be here in second carbon. Okay, and if you are looking at this position, the left one is two hydrogen atom. You can see, get it here. This is the first hydrogen, and this one is second hydrogen that is pointing down, and two phenyl group there in same plane, and you can see it here. So to get elimination, a proper elimination, it should be planar. This one, H and Br should be anti position. Now in this molecule, this H and B are in anti-position. So what I am doing now is just not redrawing, just tilting this molecule, just to tilt with some angle. You can see that this H and B are now here. You are getting in anti-position. You are just tilting this one. So you are rotating towards this direction, and you get on your right side you get phenyl and methyl, and to your left you get hydrogen and phenyl. Okay, you have hydrogen and phenyl to your left. So in presence of base, you can see in presence of base, it can attack this hydrogen, and the sigma bond break and transfer its electron to this carbon, and bromine get eliminated, and you get this product. And here you can see that the phenyl and methyl group are in same side. You can see it here in the product. Phenyl and methyl groups are in the same side, and hydrogen and phenyl group are on the same side. And in effect, these two phenyls are in opposite direction. That is, it gives E alkene, trans alkene. And this is the Sohos projection of the same compound. This one, the same Newman, I am rewriting into Sohos, and you can see here this is the beta carbon, the front carbon, this here, and you can see phenyl like this, methyl like this, and hydrogen here. And I am giving a single bond here, and bromine is down like this, and phenyl is on your right and pointing upward, and hydrogen is pointing up and to your left. And in the presence of base, this HBr get eliminated, and you can see here the phenyl and methyl group, these two groups are in same side. So you get, from this isomer, you get E product. Okay. Now just change the stereochemistry of this carbon, only this carbon, like this. I've changed the hydrogen in wedge and methyl in dash. In previous case it was, you can see here, here methyl was in wedge shape. So in this stereoisomer, we are looking this molecule from this side, and first we will write the Newman projection, and this is the first carbon atom, that's beta carbon atom. And if you are looking from this side, which groups are on your right? This one, hydrogen and bromine, is to your right. So in first carbon, hydrogen is to your right side, and in second carbon, bromine is to your right side. And what is on your left? Methyl group, and there will be one hydrogen here. You can write one, the dash shape on dash, hydrogen on dash structure. And this is on your right and pointing downward. This one, H and Br is pointing downward, and CH3 and H, this CH3 and H pointing upward. And two phenyl groups are in same in anti-position and the same plane. And this is also, we need H and Br in anti-position, but here there is CH3 and Br in anti-position. First, what we are doing is we are just rotating to here, methyl, just whole molecule is rotating. So you get a CH3 here and Br here, and phenyl and hydrogen, that is this one, and this hydrogen will be on your right side, and hydrogen and phenyl will be on your left. So you have to get this hydrogen to the ante of Br. So what you have to do is you have to rotate this methyl to here and phenyl to here, then hydrogen to here. Okay, so you get hydrogen here and a methyl here and phenyl here. This single bond, you can rotate this carbon like this. Now you have this hydrogen and Br in antiposition. So in presence of base, can abstract this hydrogen, okay, and HBr get eliminated, right? And you get this product, this alkene, where you have two phenyl groups are on same side. Okay, you can see it here. Two phenyl groups are on same side, and hydrogen and methyl groups on same side. And this is Z alkene. The previous one was E alkene. The same thing we can represent in Soh's projection like this. And this is beta carbon, and this one, this carbon, and you have hydrogen here and phenyl here and methyl here, and it is pointing downward, and here second carbon, phenyl and hydrogen pointing upward, and bromine is down. So in the presence of base, it get eliminated, and finally you can see these two phenyls are on same side even in Soh's projection. So that means it gives this second isomer, it gives Z alkene. So in short, the first isomer in the presence of base, it gives E alkene. So it is a stereospecific reaction. So second isomer, the stereomer in the presence of strong base, it gives Z alkene. So we can say the two eliminations are stereospecific. Okay, next one, stereochemistry of even reaction. And in this particular example, this compound, in the presence of sulfuric acid, it gives alkene. You get two product E and Z alkene, but 95% of you get E alkene on 5% Z alkene. So it is a stereoselective reaction, which you can say like that. So even reaction is a stereoselective. So what is the mechanism of even reaction? We already discussed. The first step, there is a formation of carbocation intermediate. So in this particular example, I can draw this structure like this. I put this molecule like this, phenyl and OH in wet shape, the hydrogen in dash, and there are two hydrogens here. One is showing here and another is showing here, and methyl and phenyl, they are in same plane. So in presence of sulfuric acid, first the lone pair on this hydroxyl group get protonated this one, and it form a hydronium ion, and this hydronium ion it expelled from this molecule and it form a stable carbocation. It is a phenyl carbocation, it's a highly stable one. So second step is the elimination of hydrogen and it form an alkene. So there are two product, geometry of product depends on the conformation about the bond. And this transition state, we can rewrite our conformation of transition state will be like this, and this carbocation will be fragonal planar carbocation that we already is sp2 hybridized, and there will be an MTP orbital, and for proper overlap this hydrogen will be in the same plane. It can donate electron density, and it finally it form a double bond by transferring two electrons from here. And there are two possibilities here. One is one conformation. There are two conformation for this intermediate, and in one conformation the phenyl and methyl group will be in the same side. So here this is if your rotating this hydrogen towards this hydrogen, this hydrogen towards here to the carbocation, and you can see that a methyl group will come here, and this phenyl and methyl group will be far apart, and therefore this intermediate will be having lower energy. And if you are rotating this hydrogen to here for proper overlap, this methyl group come towards this direction, that is a cis product will be formed. So this is the conformation we're having phenyl and methyl are on same side. This will be having steric hindrance. Due to steric hindrance, will be having higher energy. And this is the energy profile diagram of this molecule. This intermediate will be having energy like this, right? Then second one, laser pointer I'm taking, and this second one, this is a transition state structure of this molecule, this intermediate, and this is the transition state structure of this product. And finally, from this conformational isomer, you get Z-alkene. It is formed very slowly because of this steric hindrance, and there will be very less amount, you can see 5%. But here phenyl and methyl groups are far apart, and it form E-alkene, it form very quickly and will be highly stable one. So you can say the stereochemistry of even reaction is stereoselective. Okay, that's all. Thank you for watching.